Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture in Introduction to Machine Learning. Today we will extend our discussion about support vector machines. So we will cover two topics. One is kernelized support vector machines. So that helps us develop nonlinear classifiers and regressors. But up till now we have only talked about SVM in the context of classification, binary classification. So we will also introduce support vector regression. So the learning objectives for this module are: we will derive the dual form of support vector machine, and that dual form will allow us to represent data as kernels. We will replace pairs of data points by kernels, and that will bring nonlinearity into the classification or the regression task that we are planning to do. And we will also derive support vector regression objective, which we haven't covered until now. Alright, so first let's motivate the idea of a kernel. Some of it we have already seen in the previous lectures, that linear classification, for example, is not always adequate to separate two different classes for binary classification. Let's take another example. So let's say we have two features, we have feature x1 and we have feature x2, right? And these features are the two classes are spread out in this feature space as follows. So let's say we have the positive class, which is concentrated like this, and then we have negative classes which are concentrated on the two sides of the positive class. So there is no linear boundary that can separate these two classes. Now, but if I transform this feature space into another space, right? So I do a transform, and let's call this transform phi, right? And in that, let's say I have two different axes now. The axes now are phi1 and phi2, right? So what is phi? Phi is basically a function of x that transforms x into new variables phi1 and phi2. So phi1 and phi2 are the two features. It could be actually more than two features, but we will for this illustration we will take only two features. And the objective would be that we transform it into a new space where the data is linearly separable. So let's see how we can do that. One way of doing that would be that what we will do is we will define a radial basis function. So what is a radial basis function? So let's say we take this particular sample and we take this particular sample, and for this sample let's call this x1, not to be confused with the dimension x1, but let's say it is point x1. So let's say your phi1 is going to be exp, so it's a Gaussian kernel of x minus x1. Okay, we will take the L2 norm of that, we will square it, and we will divide it by some constant. Okay, so let's call it 2 sigma square. Okay, so this is your first feature, and the second feature is phi2, which is this exp of, so what is this phi? It's a function of x. Similarly, phi2 is also a function of x. And this is similarly x minus x2. divided by, so there's a negative sign here, negative 2 sigma square. Okay, then let's say that sigma is fixed, it's a hyperparameter. Okay, it's a fixed hyperparameter, and x1 and x2 are not these two dimensions x1 and x2. This is not what we are talking about. We are talking about these 2 points. So this point is x1 and this point is x2. Okay, so this is x1 and x2 as a vector x1 and x2, not as a dimension x1 and x2. All right. So for every other point x, right, we will take the distance from this point and the distance from this point, and we will fit a Gaussian kernel on that. So this is the Euclidean distance that we are looking at, x minus x1 and x minus x2. Okay. So if you look at that, what will happen is that in the phi 2 space, what will happen to all these negative points? They will have a very high phi 2, right, because they are close to, these points are close to x2 point, so they will have a high phi 2. Okay. So why? Because when your distance is small, your Gaussian kernel will give you a high value. So these points will fall somewhere here. Okay. And they will have a low phi 1 because they are far away from the x1. Okay. On the other hand, these points are going to have a high phi 1 and a low phi 2. So these points will fall here. Okay. These points will have both low phi 1 and low phi 2 because they are all far away from this particular point, so they will all fall here. Now what I can do is I can actually have a linear boundary that can separate this data. Okay. So with some transformation, I can have linear boundaries that can separate the data, which in otherwise what I would have needed is some sort of a non-linear boundary. So this non-linear boundary itself translates to a linear boundary in the new space. Okay. So that is the objective of using kernel functions. Now here if you notice that this particular function phi is defined in terms of actually 2 data points. One is the data point on which we want to compute the feature, and the second is the data point on which is a sort of a referral data point. So now you can see where I am getting at, that these referral data points are going to be the support vectors, but after we take some transformation. So this brings us to the summary of what we have just discussed. Why we want to use a kernel, why we want to use a nonlinear transform, because with the right kernel we can increase the dimension of the feature. Okay, instead of x, let's say it is 2 dimensions, we can actually introduce many phis, many different features, and the vector of features can have a much larger dimension than the vector of the raw inputs x. So now your input to the SVM is going to be not the raw input x, but the feature input, which is phi. Okay. And then it can be transformed into a space where it is linearly separable. So the example that we had already given was that we have some negative samples here, some positive samples here, and some negative samples here. So if this is x space, we transform it into using a transform into phi space. Okay, where we have the negative samples here, and the positive samples here, so that we can linearly separate that. Now it's possible that sometimes you need more than 2 dimensions of features to get that linear separability, right. So for example, if I take a different approach, if I take a different sort of data, right. So let's say my data is such that I have positive samples that are concentrated near the origin, and I have negative samples all around it, right. So now I have x1, I have x2, and I represent phi, right. So now phi of x, let's say phi of x, okay, is a vector which is x1, x2, and then x1 square plus x2 square, okay, and square root. So this is a 3-dimensional feature now, where in the phi space I have phi 1, okay, which is same as x1, I have phi 2, which is same as x2, and then I have phi 3, which is the 3rd dimension, okay, and that third dimension basically is how close are we to the origin. So in that third dimension, basically if I just look at the third dimension, let's say I want to plot now phi 1 versus phi 3, because I cannot adequately show the 3 dimensions. Let's say I want to show phi 1 versus phi 3, then the data points that I will have, they will be concentrated like this. Okay. And if there is a circle that can separate the positive and the negative classes in the phi 1 phi 3 or phi 1 phi 2 phi 3 space, it will be a line. So below that all the points are closer to the origin in the x1 x2 space, above that all the points are further away from the origin in the x1 x2 space. So I have a linear boundary in phi 1 phi 2 and phi 3 space. So that will be a linear hyperplane. I am not drawing the phi 2 dimension, but that will be able to separate the data. So many times we need a lot of dimensions, we need to transform the data into multiple dimensions to be able to find a linear boundary, possibly even infinite dimensions. Okay. So now that brings us to another point of what is a kernel, right. So kernel will be a function of two data points, it will not be a function of a single data point. So it will be a function of xi and xj. Okay. So this I'll write this as bold because these are vectors, these are not dimensions, these are vectors. Okay. So it's a function of two different data points with the following properties: that it is symmetric, okay, and it measures some sort of a similarity between xi and xj. That means it will likely have high value when xi and xj are the same, and it will have low value when xi and xj are very different from each other. Now having said that, there is another property that we want this kernel to have, that it will form a positive semi-definite gram matrix. So let's say I define a matrix K, right, and in this matrix K I have k x1 x2, k x1 x1, okay, and I have k of xn xn. What is xn? Any points, any number of points n, any number of points from the original space, okay, and a general element is k xi xj. That is a general element of this matrix. This matrix is going to be positive semi definite. What does that mean? That all its eigenvalues will be non-negative. So that means this will have non-negative eigenvalues. So if we select a kernel function that encodes similarity in such a way that any gram matrix that we find, that we form for any number of points, any n number of points taken from that space, and all those matrices are positive semi definite, then this is a kernel that can be used in an SVM. So it is called a reproducing kernel Hilbert space, and basically what has been shown is, or it is called a Mercer kernel. Mercer kernel. So what has been shown is that this k xi xj is actually some feature of xi transpose or its dot product taken with the same feature of xj. Okay. What is that phi? We do not know that yet. Okay. If we define just a kernel and that kernel is going to be it satisfies this property that its gram matrix is going to be positive semi definite, then there exists a phi, okay, there exists a phi for which the kernel function can be represented as a dot product of two features, and that phi can have infinite dimensions even. So an example of that is precisely the kernel that we looked at before, which is the Gaussian kernel or the radial basis function kernel. So it can be, example, we can have kxi xj is equal to exp of minus xi minus xj, okay, take the L2 norm of that, square that, okay, and divided by some positive constant, okay, some positive constant, doesn't matter what that constant is, 2 doesn't matter, the square doesn't matter, it just has to be multiplied with some positive constant. So I can even like delete this and say that let's multiply this with some constant k, kappa, not k, let's not confuse it, so it's some constant kappa. Alright. So this is a Mercer kernel. We can show that if we form any matrix of any size, okay, using induction, we can start with, let's say, a matrix of size 2, and then by induction we can show that if we increase the matrix of matrix by 1, it is still going to be a positive semi-definite matrix. So it's going to be the matrix is going to be the gram matrix is going to be, this is the gram matrix, gram matrix. The gram matrix is going to be positive semi-definite, and because of that it can be represented as a dot product of two features of x, and the dimension of that two features is possibly infinite, it can be more than the dimension of x itself. Okay. So that is the more important part. So now what does this point to is that we want to now change the equation of the SVM such that it can be represented as xi transpose xj as opposed to x. We want to only have dot product terms in the objective function or in the solution of the support vector machine. Once we can represent it using this, we can replace x with any phi of x, and we can replace the dot product with a kernel. Okay. So that gives us a lot of flexibility in designing nonlinear support vector machines. So the nonlinearity of the boundary was clear from the previous examples, where we showed that in the new feature space the boundaries are still linear, but in the original X space the boundaries are now nonlinear. Okay. So just a little bit of a word about the Gaussian kernel. Let's go back to this figure, this particular figure. So basically what this function is encoding is some sort of a relative distance from, or some sort of a function of a distance from some key points, and this property has been exploited before in RBF or radial basis function networks, which is a form of a neural network which we will look at later. So basically it goes back to something called kernel based estimation of functions. So let's say we have a regression, we have some regression data, so we have x here and we have the target value t here, right, and we are given several points, alright, which are t and x, they are pairs of t and x, and we want to estimate a function that smoothly interpolates these points, so that for other x's for which the training data is not given, we are able to estimate the t, right. So one way to do that is to say that let's take all these points, okay, and on all these points what we will do is we will fit a kernel function. What is a kernel function? It's some sort of a localized function, right, and this function is basically the same everywhere except that it is shifted to different training points, okay, and we will sum these shifted versions of the same function. But before we do that, we will scale this one up, we will scale this lesser, we will scale this up to this point, we will scale this up to this point, and so forth. So now once we scale these points, what we get is slightly different functions. So we get something like this, right, and when we add all of them up, the linearly scaled versions of the function, when we add them up, we get some smooth interpolated function, okay, and that smooth interpolated function is basically nothing but it is so your f of x now is sum over of I is equal to 1 to n, right, some constant kappa I, or let's say ai, times this function k of x comma xi. Okay, what is k of x comma xi? That's precisely the Gaussian kernel that was sitting, which are the yellow Gaussian functions that were so it's going to be the shifted Gaussian function, and it is shifted by the amount xi. Okay, so if we use this formula, we are able to smoothly interpolate it. We can, if these points are regularly spaced, we can have a triangular kernel which basically is the basis of linear interpolation and so forth, right? So we can have linear interpolation between these points and so forth. So there are different kernels that will give you different smoothness effects, or different kind of they are based on different kind of assumptions, right? And we can even so basically what we are doing in SVM is we are not going to use all the training points the way we are using it here. We are going to use a sparse set of points, right? And that sparseness is precisely taking out all the points that are not support vectors. So we are getting towards that, but before we get towards that, we want to change the form of the equation of the support vector machine and introduce dot products, which we will replace by kernels. We want to introduce dot products between some x and some other x, xi and xj, and we replace it with a kernel k of xi and xj. So that precisely is the kernel trick. So this kernel trick is going to make it's going to take linear problems, and it's going to still keep them linear by introducing a non-linearity in the form of a kernel. So what we will do is we'll try to change the equation, which is the primal form of support vector machine that we have already seen, and we will change it into a dual form. In dual form, there will be no single xi or single x. It will all be in terms of dot products either. So you can either think of it as xi transpose xj for some I and j, or x transpose xi, or x transpose xj, etc. But we will not have single terms of x. So once we have that, what we will do is we will assume that any dot product can be replaced by a feature vector, right? And because these feature vectors can now even be infinite, as long as what we compute is a scalar, right? So this kernel gives you a single value of comparison of xi and xj, or phi xi and phi x. So this the output of this kernel is going to be a scalar, as long as we can take these dot products and get scalars, right? And because this dot product already satisfies this Mercer kernel property, we can replace it by any kernel that satisfies the Mercer kernel property, which means that its Gram matrix is a positive semi-definite. So we will use that, and that is called the kernel trick. We will replace all the dot products with a kernel. Okay, so now let's see how we can change the original SVM objective function into its dual form, where everything will be a dot product. Okay, so let's start with the hard SVM. So the objective is over weights and biases, okay, weights and the bias of the SVM, and it is basically half of this W square, right? So we are trying to shrink the weights, right, and while keeping the margin constant. And what we will use is we will use the Lagrange form of the constraint, and the Lagrange form is that we will have a sum over I. Okay, these are all the data points, and we will have the Lagrange multiplier AI. Okay, and we will have this training point Ti. Okay, and then W transpose Xi plus B. Okay, minus 1. Why minus 1? Because the margin is minus 1. Okay, and with subject to the constraint that AI, all AIs are greater than or equal to 0 for all I. Okay, so what is this? This is basically the Lagrange form of the constrained optimization over W. We are trying to shrink W. We are trying to shrink the mod of W, okay, the L2 norm of W, and it is subject to the condition that for all training points this particular expression should be greater than or equal to 1, okay, or in other words this expression minus 1 is greater than equal to 0. So from Lagrange multipliers what we know is that, let's say we have some Lagrange multiplier over some variable x, okay. We have a Lagrange function, right. So what this function encodes, let's say this function is f of x plus lambda g of x, okay, lambda greater than 0, okay. So this function encodes, so if we want to minimize this function, we are encoding minimizing f of x subject to g of x is greater than equal to 0. These two so minimize this first form and this second form are equivalent. Okay. Why are they equivalent? That basically goes back to the Lagrange multipliers. So let's say if we have an x space, this is x1, this is x2, okay, and if we look at f of x and we plot its contours, values, the contours of equal value, right, and let's assume they look like this, right, and what we want is we want gx to be greater than equal to 0. So now let's change the color and let's draw the boundary of gx equal to 0. So let's say gx is equal to 0 is this boundary, and this side of the boundary is gx greater than equal to 0, the other side is gx less than equal to 0. So now what we want is we want the solution to lie on the right side of this red curve while it finds the minimum of the yellow curves, right. So what we will want is that yellow curve, the solution will be at a yellow curve that is tangential to the red curve. Okay, let me draw it in a green color so that it stands out. So this green color is one of the yellow curves. This green is the ideal yellow curve because it is tangential to the red curve. At that point we will achieve the solution where the two curves are tangential, okay. And that is easy to see that for all the other yellow curves other than the green curve, right. So either the gx greater than equal to 0 is not satisfied or the minimization of fx is not satisfied, right. If you go to any green curve that is outside, any yellow curve that is outside of the green curve, then fx is a larger value. If we go towards the left, then fx is smaller value, but it will never touch this gx is equal to greater than equal to 0 boundary, okay. So how we get to this Lagrange equation is that if you want to minimize this, we will take its derivative and set it to 0, and that vector derivative is going to be, the vector gradient is going to be 0 only when the derivative of fx and derivative of gx are in the same direction or opposing directions. They are either aligned in with 0 degrees or 180 degrees. So that means what we will have is that we will, with a constant lambda, we can cancel the two out and we will get the derivative equal to 0, okay. So for based on that you can see that this Lagrange multiplier will give you the constrained optimization equation. So now let's go back to the W space instead of this X space, and this X is by the way different from, this is just an example X space. So let's draw a boundary around it, we don't need it anymore. Now let's go back here to the W space. The first objective that you see is basically equivalent to minimizing mod of W square subject to multiple constraints where Ti times W transpose Xi plus B is greater than equal to 0, okay. So it is precisely the hard SVM objective that we are trying to minimize. Now if we do that, what we need to do is we want to basically get all the X in that equation out and we want to replace them, we want to convert it into a dual form where it is only X transpose X, okay. So for that what we will do is we will have this new objective function now, with the Lagrange multipliers also, right, and this is what we had in the previous slide. Okay. So for this particular objective function which we want to minimize, okay, we will set the derivatives of L with respect to W equal to 0. Okay. So when we set this derivative equal to 0, what we will get is the value of W, the exact value of W for which we get the minimization, and that is precisely sum of all I, okay, of AI, Ti, Xi, right. So how do we get that? Let us say if we take the derivative equal to 0, for this particular one we will get the first term we will get half of 2W, right, and here we will get negative of, so B will not matter because there is no W here, we are taking derivative with respect to W equal to 0, and that will be 0 for the B term, right, and it will also be 0 for the -1 term. What we will get is AI, Ti, and then derivative of W transpose X will be Xi. So when we solve for that, we will get the weight is equal to AI, Ti, and Xi, sum of that for all I. Okay. Similarly, when we take derivative of L with respect to B and we set that equal to 0, what we will get is this equation where you will have sum over I of AI, Ti. Okay. So now we can plug these two in back into the equation to eliminate both W and B. Okay. So what we will get is the objective in terms of A, okay, just in terms of A, and that will be summation of I of AI once we plug that back in, and then we will get half, okay, of sum over all I, and then sum over all J. I will tell you where the J is coming from, okay, and we will get AI, Aj, Ti, Tj, and then X transpose, Xi transpose Xj. Alright, and so once we minimize these, we will get the values of AIs, right, and that will give you the equation for the SVM. Now where do we get the J from, right? There was no J earlier. So what you can see is that the value of the weight has one summation running over all the training points. When we plug it back in, right, when we plug it back in here and here, right, especially when we plug it back in here, it is going to be a summation over all training points, and we have another summation over all training points. So we will get two summations, and they will be two separate indices, one is I, the other is J. That is how we get the summation over I and summation over J. If you can derive it on your own, it's not that difficult, it's pretty straightforward. Just make sure that when you plug the value of W here, right, let me change the color. So when you plug the value of W here, this summation is going to become a summation over J, okay, because it's not the same summation that you have here. These are going to be two different summations. Both will be running on all training points. So one will be over I, index I, the other will be over index J, so that we want to have non-same index pairs like Xi and Xj. So once we have that, this is the equation that we will get, okay. And if we want to compute the output, that output is going to be sum over all I, okay, for any particular input X, it is going to be sum over all I, AI, Ti, okay, and X transpose Xi, okay, plus B. And we can plug in the value of B whenever we can solve it. So notice a couple of things here. So here we have been able to change the equation so that x does not appear alone, it actually appears as pairs of training points. So we are looking at pairs of training points xi and xj, whereas once we are computing the output for any test case, okay, any test case x, right. So for that we have been able to convert the same equation into its comparison with every training point. So this is test and this is training. Now are we comparing it to every training point? Well, no, we will have some AIs will be 0, AI is greater than or equal to 0, for some training points AI will be exactly 0, and those training points will not be a part of the equation, a part of this summation. And what that means is that they are not going to be support vectors. If A is greater than 0 strictly, then they will be part of this equation, and because of that those will be the support vectors. But here now, because we have this transpose, we can or the dot product, we can replace this by kernel function of xi and xj here, and here we can replace it by kernel function of x and xi. Okay. So that is precisely the dual form that we were hoping for, and now we can replace this kernel function by any function that basically is a Mercer kernel, which basically satisfies the property that its Gram matrix is positive semi-definite. Okay, so now let's get back to the Lagrangian a little bit and look at some conditions that come because of the Lagrangian. So let's start with the original formulation that we were looking at, the canonical representation of Lagrangian. So let's say we were looking at Lagrangian of x, and basically it was about minimizing f of x, okay, subject to the condition that gx is greater than or equal to 0. Okay. So what we found was that if we minimize this, it is equivalent to minimizing fx subject to that condition that gx is greater than or equal to 0, is same as working with this particular minimization. All right. And what this implies is that your solution will be such that either gx is greater than or equal to 0, okay, all these conditions will be satisfied. So gx will be either equal to 0 or greater than 0, and it will never be less than 0, because that's what we want. We don't want gx to be less than 0, we have an inequality constraint. Then we will have lambda greater than or equal to 0, right, and then we will have lambda times gx will be equal to 0. So what that means is either gx is 0 or lambda is 0. So what does that mean? So if we go back to that drawing that I had of these yellow curves, right, so the center of the yellow curves is the minimum of fx if there was no constraint, okay. And then we drew a red curve which basically represented the boundary of gx is equal to 0, and we thought that, so now there are two possibilities, right. So one possibility is that the gx greater than 0 lies in this direction, and the other possibility is that I will draw the same thing, but gx greater than or equal to 0 lies on the other side. So let's say it's the same contours and it's the same boundary for gx equal to 0, but gx greater than 0 lies on this side. So this is gx greater than 0, and here gx greater than 0 is on the other side, right. So for both these conditions, the math works out slightly differently, the inequality works out slightly differently. Now if you imagine, if you look at the first case, we already looked at that, where we saw that the ideal solution will be such that the ideal solution will have a will be tangential to the gx, right. So it will be tangential to gx equal to 0, right, and on that ideal solution the derivative, the gradient direction of and the gradient direction of gx, they are going to be 180 degrees opposite of each other, and because of that they will cancel out, sorry, not they will be aligned, they will both be in one direction, they will both be, if we go in this direction both of them will have the maximum increase. So if we add them using a constant, we can basically put the joint gradient to be equal to 0. Okay. So for that particular case Gx is greater than 0, alright, and because the two have to cancel each other out, lambda will not be 0, lambda will also be, sorry, Gx will be equal to 0. So case 1, case 1, case 2. So this is case 1, this is case 2. Okay. So in case 1 what we will have is that your Gx is going to be 0, Gx is equal to 0, alright, and consequently your lambda is not going to be 0, so it is going to be greater than 0, but because Gx is 0 we will add, when we multiply the two we will get lambda times Gx is equal to 0. Case 2, when Gx greater than 0 lies in the same region, it lies in the same region where the fx, unconstrained fx is minimized, right, then Gx actually does not matter, we are just minimizing fx, that means lambda is 0. So in this case you will have lambda equal to 0, okay, and Gx will be greater than 0 because we are not on the red boundary, we are on the left side of the red boundary, and because of that, because lambda is 0, again we will have lambda times Gx is equal to 0. Okay. So for the conditions on the right are satisfied for both the two cases. So what this means is that if we go back to that objective function in terms of A, which was, let me see if I got all the terms correct, ai, right, minus half sum over I and sum over j. Which was equivalent to what we had earlier, right, where we had this LWBA, right, where we had half of mod W square, right, minus sum over I, AI, Ti W transpose Xi plus B minus 1, right. So these two were equivalent optimization problems that we were looking at. Now the three conditions that we looked at where Gx is greater than equal to 0, lambda greater than equal to 0, and then the product of the two is going to be equal to 0 because we will have one of them equal to 0 in both cases. So what we will get here is that AI will be greater than equal to 0, we know that already by definition, okay, and then we will have training point, okay, times y of xi, y as a function of xi, okay, minus 1 is going to be greater than equal to 0, and the two together ai times ti this will be equal to 0. So these are the three conditions that will be satisfied for this formulation of SVM. Okay. So because of this, what we can get is we can get different conditions to solve for W and B. So W we already eliminated, but we can get B now. So because of this, what we can get for B is that Ti is going to be sum over all the points that belong to support vectors where ai is non-zero or aj is non-zero, okay, we will have aj, okay, Tj xi transpose xj plus b equal to plus b, this summation will be equal to 1. Sorry, Ti times. And when we solve for this, what we will get is b is equal to, okay, so we are not counting any of those where ai is equal to 0, number of support vectors, okay, sum of I belonging to support vectors, the set of support vectors. So what are set of support vectors? ai greater than 0 implies support vector, okay, that means that xi belongs to the set S, okay, implies xi, the training point xi belongs to the set S, okay, and for those points exactly this will turn out to be equal to 0, not greater than 0, it will be equal to 0 because it is on the margin, okay. And for these points we can define the bias in terms of these points, and it will be Ti minus sum of all the points belonging to the support vector. So notice that we are taking pairs of support vectors now, because everything will be in terms of dot products. So we will have aj tj, okay, and times what I cannot write it here is xi transpose xj, and that will be the bracket close. So that will be the value of the bias b, okay. So this basically completes our derivation of the dual form for hard SVM, okay. So this hard SVM is basically completely solved in terms of dot products. Wherever you see xi transpose xj, you can replace it by k xi xj, and wherever you see x transpose xj, you can replace it by k x xj, right. So that is, and you can plug in any kernel. Now let's look at some example kernels. Okay, before that, let's quickly look at the KKT conditions. These are called Karush-Kuhn-Tucker conditions, the three conditions that I talked about, okay. So how do we interpret this? Wherever you have a equal to 0, those are the support vector points, okay, sorry, those are the points that are not support vectors, do not belong to the set S, the set of support vectors S. So for these points, okay, this particular condition need not be 0, it can actually be greater than 0. What that means is that they are further away from the margin, okay. These points do not define the boundary of the decision boundary, because for them ai is 0. These points can be moved around, so long as they do not cross the margin, they can be moved around anywhere, and the boundary of the support vector machine will not change. On the other hand, if we have ai is greater than 0 or an is greater than 0, then necessarily the other condition, the other KKT condition will be satisfied, which is that they are on the margin, and we will get this expression equal to 0. These points define the boundary, so these are support vectors, okay. And if we move these points, then we have to retrain the classifier, we have to re-estimate the boundary of the support vectors, the boundary of the classifier, and these are the support vectors. So now let's see how we can replace x transpose x, xi transpose xj with k xi xj, right. So if we do that, we will get, so let's say if we have a Gaussian kernel, then how does that change the boundary, right. So what is k xi xj? Basically for Gaussian kernel it is going to be exp of minus some kappa, some constant kappa, okay, xi minus xj, okay. So that is basically the Gaussian kernel. So what will happen is, let's say we have the x1 x2 boundary, okay, and we have some positive points and we have some negative points, lots of negative points, lots of positive points. Okay. So because we are only interested in those points for which AI is greater than 0, right, those are the only points that are support vectors, and they might look like something like this. Those will be the points that are closer to each other in some sense, not in the linear sense, not in the linear Euclidean distance sense, but in some sense. So hopefully it will be this point, perhaps this point, perhaps this point, and this point. Okay. So now think about a Gaussian kernel sitting on top of these points. So basically what we have on these points is we have some Gaussian function that is decreasing around them, right, and that defines a 4-dimensional feature space, right, which is basically the Gaussian kernel as defined by the distance from these 4 points. Okay. And some linear combination of that when it is equal to 0, that will be the decision boundary. So your decision boundary will be something like the following, right, and that decision boundary is going to be linear in the phi space, but it is going to be non-linear in the x space. Okay. So this smooth some sort of a smooth surface around a sparse set of points, a subset of points which are the support vectors, and then using those smooth functions, the smooth surface in some sort of an isotropic way. Isotropic means that in whichever direction we go, there will be a smooth degradation of the contribution of that point, smooth decrease in the contribution of that point. Using that is what is being done by a Gaussian kernel. Now there are other kernels that are also useful, not just Gaussian kernel. There is something called a polynomial kernel, for example, right, and in polynomial kernel you will have xi transpose xj plus some constant c and to the power d. Okay, so d is the degree of the polynomial. Okay. You can have a cosine kernel where you have xi transpose xj, okay, and then divided by the L2 norm of xi, the L2 norm of xj. Alright. So there are multiple different kernels. These are some of the useful kernels, and you can have a linear kernel which is just xi transpose xj, which means that there is no non-linear transformation. You will just find a linear boundary in the xi xj space. So all these kernels together define are useful in different ways. Now the advantage of these kernels is that not just that we have these 3-4 popular kernels, but you can actually define your own kernels depending on the data. So let's say you are comparing 2 different texts. There are kernels that are defined for comparing texts. So what the kernel is encoding is how similar are xi and xj to each other. So if they are more similar, then xi will have more contribution in computing the output for xj. If they are less similar, then xi will have less contribution in computing the output for xj. So this goes back to that kernel interpolation that I showed for regression couple of slides ago, right. So that similarity is being coded by this function, and the similarity you have a lot of flexibility in defining what is similarity, so long as you can define it in some sort of a positive semi-definite sense, symmetric positive semi-definite sense, right. So symmetricity is actually a part of the positive semi-definiteness. So you can also have kernels that compare 2 different graph data, for example. So there are different kernels, and that's a little bit out of scope for this course, but just suffice it to say that you have to find a kernel that adequately represents some sort of a notion of similarity for the data that you have. If the similarity is in a Euclidean distance sense, then perhaps Gaussian kernel will be fine. The radial basis function Gaussian is also called RBF, radial basis function kernel is going to be fine. If it is something else, you might want to find out what are good kernels for a different type of data or for a different notion of similarity. So until now we were looking at hard SVM, where we assumed that the points to be classified were separable, right. So if we have non-linear boundaries, then in general we should be able to separate any kind of data given the expressiveness of the kernel. If we choose a kernel like a radial basis function or which is also called a Gaussian kernel, we should be able to separate all the data points. But the problem what happens is that it sometimes divides the input space into many small fragments, and those fragments are not desirable. So although the data may be separable in a nonlinear sense, we may not completely want to separate it, and we may want the boundaries of the support vector machine to be smoother. So that smoothness is basically precisely what regularization is all about. So we will just assume that they are not separable. We want to allow for some misclassification. So if we want to allow for some misclassification, what we saw in linear SVM is that we introduced slack variables, and those slack variables were allowed to have value greater than 0 for the points that were intruding into the margin and greater than 1 even when they were misclassified. But we wanted to minimize the overall number of points that were misclassified, including their absolute distance from the misclassification boundary and from the margin itself actually, while putting a constraint on the mod of W. We didn't want to we wanted to be able to do a trade-off between how complicated, how many points are misclassified versus how small is the norm of W, or how large is the margin. Okay, so we will have an error function. We won't have an error function that will give an infinite error upon misclassification. We want some finite misclassification error. So basically, just like in the linear SVM, we will have a slack variable xi, which will be greater than or equal to 0 for all points, okay, such that it is 0 if the point is on the correct side of the margin boundary, and it will be greater than 0 if it intrudes into the margin or it is misclassified. Precisely, it is going to be t times mod of t times t minus yn. So that formulation now changes slightly from the hard margin SVM. So what we will have is the loss function will be in terms of WB, and now we will have A and mu. Okay, so I'll show you what mu is. Basically, it comes in with the slack variables. So as before, we will have half mod of W square, okay, norm of W square. Right. And now what we will introduce is we already had this, right? We had I, right, AI, right, and then we had times Ti y of xi, right. Then we had -1, right. So we will have that -1, but then we will also have this slack variable xi, okay, and this will be the close bracket close, okay. So here we have another inequality. That inequality is that this slack variable is greater than or equal to 0. So what we will have is, so first of all we will have we want to minimize the sum of the slack variables, and we want to enforce that all the slack variables are greater than or equal to 0. So where does this come from? This is Lagrange multiplier for the condition that each and every xi is greater than or equal to 0. Okay. And where does this C come from? This C comes from the trade-off between W and minimizing the xi's. This is like the lambda that we had for the hard SVM, right. So instead of lambda, we are saying it is going to be C here. Okay. So now if we solve this, the KKT conditions will be slightly different. Earlier we had 3 KKT conditions, now we will have 6 KKT conditions because we also have the Lagrange multiplier over xi I. So the 6 conditions are going to be AI is going to be greater than equal to 0, okay, Ti times Yi Yxi, right, minus 1 plus xi I is greater than equal to 0, and then the product of the two is going to be equal to 0. So that is straightforward. Okay, so these are the 3 original KKT conditions, except that instead of just minus 1 we have minus 1 plus xi I. Okay. Now we will have 3 other KKT conditions from the condition that xi I is greater than equal to 0. So one will be that all the Lagrange multipliers mu I are greater than equal to 0, the Lagrange coefficients, and then we will have xi I greater than equal to 0, right, and then whenever mu I is 0, xi I is strictly greater than 0, whenever mu I is greater than 0, then xi I is strictly equal to 0. So we will have mu I xi I equal to 0. Okay. So using this 6 conditions, we can now eliminate W and we can have everything in terms of the dot products of xi and xj. Okay. Once we eliminate W, W itself will be based on a summation of xi, and when we plug that in into Yxi, which is W transpose xi plus b, what we will get is xi and xj's together, right. So similarly what we have as before, we will have del L by del W, okay, equal to 0, and that will imply that W is equal to sum over I Ai Ti Xi, okay, and then del L by del B equal to 0 will imply that sum of Ai Ti is equal to 0, right, and then del L by del the slack variable I equal to 0, that will imply that Ai is equal to C minus mu I. Okay. So we will substitute this back and we will see how this eliminates xi and W and B, and we will get everything in terms of A and mu, and basically we will also get as a consequence of that the dual form of soft SVM, where instead of single xi's we will have dot products of, it's a different loss function in terms of just A is going to be sum over I Ai, okay, minus half sum over I sum over j. These are all training points, pairs of training points now, including the training point with itself. We are going to get Ai Aj Ti Tj, similar to what we had for the hard SVM, Xi transpose Xj, alright, and the condition that we will get is 0 is less than equal to Ai is less than equal to C, okay, and we will also get sum of Ai Ti equal to 0. So these conditions that A can only be between 0 and C are called box conditions. So A is boxed into 0 and C, okay. So what does this mean? What does it mean that A is boxed? So basically we have 3 types of A's for all points. We have points where Ai is 0, so that means those points do not affect the equation. They will the term inside the double summation is going to be 0 for those AI's or AJ's which are 0. Those are precisely those points that are not support vectors, they do not matter. And then there are points that are going to be C, right, and then there are going to be points that are between 0 and 1, okay, 0 and C. So let us look at this. So whenever ai is equal to 0, okay, then basically your xi I is going to be less than equal to 1. Okay. So these are the points that are correct but in the margin. But inside margin. Okay. When ai is equal to 0, okay, then they are these are ai greater than 0, and whenever ai is equal to 0, that means they are on the correct side of the margin. So these are not support vectors, not SV. All right. And then we have whenever ai is equal to c and xi I is greater than equal to 1, that means these are going to be the incorrect points, incorrectly classified points or misclassified points. Okay. So here it is going to be ai is less than c. Alright, so these are the three different types of points that are defined by this dual form of the SVM. And again we can replace x transpose x by k of x and x, okay, two different x's, and we can further derive it to find out for any particular point x how we will compute what the y is in terms of ai and aj for all the training points. Actually not all the training points, only the points that are going to be support vectors for which ai is going to be greater than 0. Okay. So that's pretty much it about the hard SVM. The only thing that is left now is to basically analyze this further, and then we will talk about support vector machines, right, support vector regression. So here the minimization we already talked about is that L dash of A, which we showed previously, and basically what we have in C, right, C is now your hyperparameter. C is a trade-off between your slack variable penalty and the margin. So what that means is that if you have a large C, then you are putting more and more constraint, more and more emphasis on reducing xis. That means you are putting more and more emphasis on having fewer misclassified points, okay, and you are not putting a whole lot of emphasis on increasing the margin. So if you don't increase the margin, then basically you are putting more and more emphasis on what do you call it, it's more and more emphasis on correct classification, and because you are putting more emphasis on correct classification, you are going to have more support vectors. On the other hand, if you allow fewer support vectors, you may have misclassifications, more misclassifications, but your boundaries are going to be smoother. So again, it's important to revise what are these different types of points for the box constraints. So if you have an equal to 0, then the points are inside the margin and they are correctly classified. If they are greater than 0 but less than c, and but your xi variable is 0, then they are on the margin. If an is equal to c, all right, and but xi is less than equal to 1, then they are correctly classified but they are across the margin, and then these are the points that are incorrectly classified. Okay. So to give you to write it more concretely, so let's say this is your these are your axes and this is your decision boundary, and this is the margin, and let's say this is the positive side, this is the negative side. Let's just talk about positive points. For positive points, here an is equal to 0, these are these points. The points on the boundary are these points for which an is not 0, it is greater than 0, but it is not C yet, okay, it has not become C yet, okay, and xi is still 0, slack variable is still 0. Anything on this side, xi is going to be, anything across the margin, xi n is going to be greater than 0. Okay. Up to the boundary, xi is going to be less than equal to 1. After the boundary, it is going to be greater than 1. All right. And any point that intrudes into this space or gets misclassified, for that an is going to be exactly C. Now, the good thing about this formulation is that every point that intrudes into the margin or goes across the margin, its influence does not increase, its influence always remains C. Okay, it is capped by C, so that is the box constraint. So what this means is that there is some sort of natural tolerance for outlier points. So if a point becomes noisy and it is like somewhere very far away from the boundary, its influence on the boundary is same as any point that has intruded into the margin. It doesn't matter how far it has intruded. So that is capped at C. And this C can be the hyperparameter that we tune, okay, and you will see that there are other ways of formulating the hyperparameter, the trade-off hyperparameter, okay, that will tell you about the trade-off between number of support vectors and the smoothness of the boundaries in the X space. So here I have just drawn a linear boundary because I have not used the kernel, but ultimately what you will have is a kernel also. So what you will actually have in the X1, X2 space, okay, let's say you have a bunch of positive points and then you have a bunch of negative points, right. So some of these, how many of these points, so let's say there are some points that are misclassified, right, there are some points that are noisy. Let's go back here. So let's say there is a negative point here, there's a positive point here, okay, these points came because of some mistakes, right. Now, do we want a boundary that basically goes like this? Okay, if you want a complicated boundary like this, then we need a lot of support vectors, right. Those support vectors are going to be like this one, basically the points that seem to be close to the boundary. So if you are assuming a Gaussian kernel, these might be the support vectors, right. So it's a very complicated boundary, and it is not tolerant to this noise that we saw in these 2 points. Instead, if we want to right, so like a boundary like this, right. So this is not a noise tolerant boundary. On the other hand, if I draw, let's say, similar type of points in and use a smoother boundary, and let's say this is misclassified and this is misclassified, right. A smoother boundary might look like the following, just this, right. So if we just have a smoother boundary like that, we will have fewer support vectors, okay, and perhaps this is going to be a support vector, this is going to be a support vector, because anyway it's far from the boundary but it is misclassified. So for this an is going to be greater than 0, but it will not exceed C, and let's say perhaps just a few number of support vectors, and I will get a noise tolerant boundary which is smoother, and that has a more regularization effect on the classifier, okay. So that is how the kernels, the trade-off between how many support vectors you have works when you change C, okay. Now in many of these kernels there is a second hyperparameter, right. So C is one hyperparameter, okay. So which are the hyperparameters? One is the C itself, that is common to everyone, but now for kernel specific, hyperparameter can be for example the sigma or the kappa that we had for the Gaussian kernel, or the degree that we had for the polynomial kernel. Okay, so those are going to be kernel specific hyperparameters, and the best classifier that you can find is that gives you, you will try different values of hyperparameters using some sort of a grid search. So you will have, let's say, C, and you will have kappa, okay, and you will have certain values of C, 0.1, 1, 10, right. So 3 different values of C, 3 different values of kappa, 0.1, 1 and 10, and so you have 9 different combinations to try, and you will try these 9 combinations on validation data, the one that gives you best results on the validation data. So let's say this one gives you the best result on the validation data. That combination is what you are going to use on the test data. So that validation and hyperparameter tuning using grid search, those ideas that we learned in machine learning for smart monkeys or linear classification, those are also valid here. So again, let's revise what points define the boundary. Those points where xi equal to 0 are on the margin, right, and but an will be greater than 0 for these points. They can be between 0 and 1, xi n can be between 0 and 1, or it can be greater than 1. So xi n is equal to 0 for points on the margin as well as points that do not matter, the non-support vectors. Okay, so the computation of yn will remain the same as we saw for the hard SVM. Now let's look at the last topic for support vector machines, and that is support vector regression. Now this is a slightly mind-bending idea, so look at it a little bit more carefully. We'll start with the linear concepts and then we will go into kernels. Okay, so let's first start with the classification problem. In classification problem, let's say you have an x1 x2 space, and our objective is to find a boundary, okay, such that all the positive points are on one side, all the negative points are on other side, and they do not intrude into the margin. So all the positive points are here, some of them are on the boundary, all the negative points are here, some of them are on the boundary. So these are the support vectors, they are on the margin. So this is classification, support vector machine classification. On the other hand, what we have for regression is we have, let's say, y and x, right. So this is x, this is y, or t, what we want to predict, right. Here we want to find a line, right, such that there is a margin around the line, okay, and all the points, there is no positive point or negative point, all the points are inside the margin, all the points are inside the margin, they are almost as if there is a band around the line and they are roughly following the line. The points that are on the margin, okay, these are the support vectors, right. So there is no point outside the margin, it's a regression problem. So this is a regression problem. Okay, so we have now two slack variables. So here we could fold this space, right, we could fold the negative space onto the positive space, we could use this as a mirror and or a fold in a paper, and we could fold it over by multiplying with Ti. So Ti is -1 on one side and +1 on the other side. If we multiply W transpose Xi plus B with Ti, we are folding it on the boundary so that everything is now positive when multiplied by Ti, right. So we don't have that advantage in regression. We have points that can go outside the margin above a line, or below the line they can go outside the margin. So we now need two slack variables, one for above the line and one for below the line. Okay, so your error, so basically we are going to have a noise tolerant. Let's go to the next slide. So what we are going to say is that our loss is such, right, that, so this is what, this is your loss, okay. And what is the loss? Loss is on loss is going to be on this Ti minus Yxi. So our loss is going to be tolerant, there will be no loss as long as we are inside the margin, but outside the margin there is going to be a loss. Okay. So up to plus epsilon and minus epsilon, between minus epsilon to plus epsilon we have no loss. These are all the points that are close to the line. Okay. So this is for regression. And by comparison for classification, our loss was like this. Okay. So it's similar, but except that we have a small noise tolerant region where it does not matter if the point lies. Points that lie on the boundary here, here or here, those are the support vectors. Those that lie inside are not the support vectors, and nothing lies outside. Or we can even formulate it as a soft margin regression where some points are allowed to lie outside. I will not go into soft margin regression, it's just a straightforward extension of soft margin classification. Let's just look at the hard margin regression, and then we will leave it at that. The dual form can also be derived very easily from that. Okay. So here we will have the mean square error. So if we have regular regression, we will have mean square error, right? So mean square error is going to be half of sum over I, okay, yi minus ti whole square, okay, plus some regularization term mod of lambda w square. So this is mean square error for linear regression. Instead, for support vector regression, the loss is going to be that we will have some c times I, okay, yi minus ti, sorry, we will have this expression, the loss E epsilon, okay, of yi minus ti. What is E epsilon? This is precisely E epsilon. This red curve is E epsilon, okay, of yi minus ti. So I will just call it yi minus ti, yi minus ti. Okay. So E epsilon of yi minus ti plus half mod of w square. Okay. So these are two different ways. The first one is not for support vector, the second one is for support vector regression. The first one is for regular linear regression that is solved using mean square error, right. So here this E epsilon is nothing but the red curve that is drawn above. So here your E epsilon of yi minus ti is equal to max of 0 comma yi minus ti mod minus epsilon. Okay. All right. So now we have two slack variables. Okay. One will be xi, the other will be xi hat. Let's say it will be xi hat. So basically what you will have is ti is less than equal to yi plus epsilon, okay, plus the first slack variable xi, and we will have ti will be greater than equal to yi minus epsilon minus xi hat of I. This is the second slack variable. Okay. And basically your objective can change to C of sum over I xi I plus xi hat of I, okay, plus half of mod w square. So see the difference between C and lambda is that they are just inversely related to each other. you can, what C does, that's the same thing as what 1 by lambda does. What lambda does is the same thing as what 1 by C does. So it's they are just equivalent. It's just a matter of preference that whether we put the hyperparameter as C or as lambda. They are just equivalent, just reciprocal of each other. Now here the xi and the xi hat is basically saying that this particular loss function is made up of this curve and it is made up of this curve. So let me remove that. So basically it is made up of this curve plus this curve, right. So these two curves are, one of them is the xi, the other is xi hat, right, and they are both greater than or equal to 0, and they are defined in to find points that go above the margin or below the margin of that regression line. Now it is regression, right, not classification. So this same analysis we can converting it into a dual form that we did, we can do that dual form for epsilon for regression also, and based on that we will get everything in terms of dot products, and then we can replace that dot product with a kernel, and we can get non-linear regression for support vector machines. So I will leave that perhaps as an exercise in one of the tutorial sheets for you to look at. All right, thank you.